So, today I will discuss about the effect of magnetic field on hydrogen like atom. So, that is basically effect of magnetic field in the hydrogen like atom. So, that is basically Zeeman effect. So, already we have seen earlier, but now what I want to do that using the quantum mechanics, how we can get the how we can explain this Zeeman effect. Okay. So, Zeeman effect is nothing but the splitting of spectral lines in magnetic field, and we know this without magnetic field. What is the Hamiltonian? Basically Dirac Hamiltonian for hydrogen like atom. So, that is H equal to H 0, that is non-relativistic and spinless Hamiltonian H 0. Then relativistic term H relativistic dash, then LS coupling term, okay, plus Darwin term, that we have seen earlier for hydrogen like atom. What is the Dirac Hamiltonian? Okay. So, so this LS coupling, that HLS, that is a function of R L dot S. Okay. This specially this I have written because this has importance for Zeeman effect. And when we apply magnetic field, then additional interaction energy is called magnetic interaction energy, that is basically mu dot B. So, two kind of magnetic moment is there for electron in hydrogen atom. One is this mu L, angular magnetic moment. So, this energy, corresponding energy will be minus mu L dot B. Similarly, for spin magnetic moment, that will be minus mu S dot mu B. So, these two term due to magnetic interaction. So, these two term in Hamiltonian it will be included. So, so total Hamiltonian for hydrogen like atom in a constant magnetic field will be this H 0, this is H 0 plus this LS coupling term, we kept it, and then plus this E by 2 m, you know this mu L equal to minus E by 2 m L, and mu S equal to minus G S E by 2 m S, okay, G S equal to 2. So, basically this Hamiltonian term, that is if I write del H B due to magnetic field H B dash, that will be E by 2 m L plus 2 S, because G S equal to 2. So, 2 S dot B. So, that will be the Hamiltonian term for the magnetic interaction. Now, here I have excluded the relativistic term and the Darwin term, because these terms are small compared to the magnetic interaction term. Okay. So, that is why in this case we have neglected, because this magnetic field is such that it's not very weak field. It is such that this term, this energy term or term in Hamiltonian magnetic interaction term, its strength is quite high compared to this relativistic term and Darwin term. So, so that is why we have neglected this term, but when this term magnetic interaction term will be weak, small, or it is comparable to H relativistic and H Darwin term, then one has to consider this. So, here I assume that this field is not very small. So, this term is appreciable, okay, and it is higher than this this relativistic and Darwin term. Okay. So, that is why I have written complete Hamiltonian for this hydrogen like atom in a constant magnetic field. So, this the the H 0 basically, this is the LS coupling term and this is the magnetic field interaction term. Okay. So, now you have Hamiltonian for your system, means hydrogen like atom in a magnetic field, constant magnetic field. So, one has to solve basically Dirac equation. So, Dirac equation will be H psi equal to E psi, right. So, nature of solution depends on this HLS term. So, we can put condition that whether HLS term is greater or less than magnetic field interaction term. Okay. Now, let us consider the case where this magnetic field is very strong, where this magnetic field is very strong. Okay. So, that means strong field. How strong it is? Now, generally we tell this B should be greater than Z to the power 4 Tesla. Okay. So, if B magnetic field is very strong, then we basically see the Zeeman effect, that is called normal Zeeman effect. So, this HB dash term means magnetic interaction term, that is now that is very very strong. So, compared to this HB term, this LS term is very very small. So, one can neglect this one in case of very strong field. So, LS term also one can neglect. Okay. So, ultimate Hamiltonian will be H 0 plus HB dash. Okay. So, H 0 is as I told that this is the basically Schrodinger Hamiltonian for it is the non-relativistic and spinless Hamiltonian. So, if we consider that magnetic field is applied along Z direction, so magnetic field is parallel to Z direction, then we can take basically Z component of L and S. So, we have written EB by 2m, B is along the Z direction and then L dot B means we have taken component along the Z direction. So, LZ and then plus 2 SZ. Okay. So, under the circumstance, under the condition, now ultimate Hamiltonian for hydrogen like atom in a very strong field. So, this is the Hamiltonian. Okay. So, this to get the solution for this Hamiltonian. So, we will use generally we use perturbation. Okay. In case of perturbation, generally we have to consider unperturbed term and then the correction term perturbed term. Okay. So, here one can consider H 0 is unperturbed term and this interaction term can be perturbed term. Okay. So, already we know the solution of this H 0. So, H 0 that is if we apply on this wave function. So, energy will be E n, where E n you know this minus mu z square e to the power 4 divided by n 2 n square h cross square. Okay. So, for H 0 we know the energy, also we know the wave function. Okay. So, that already we have solved and this is known to us. Now, this wave function now will be used for calculating this correction term, Potter term. Okay. So, how to calculate that already know. So, if we see that this in this term whatever it commutes, this operator it commutes with the H 0, then this psi n l m l m s will be simultaneous wave function and we will get the eigen value for this operator L z and H z. And it is true that L z and H z is commutes with the H 0. So, this psi n l m l m s, this basically wave function of L z and H z also. So, if we apply L z on this wave function, so you will get the eigen value, that is m l h cross, and for H z it will be m s h cross. Okay. So, if you basically apply this Hamiltonian on this wave function, so that equal to basically we will get the energy value E, and that energy value E will be E n plus E b by 2 m m l plus 2 m s h cross. Okay. So, now final energy level, whatever initially it was E n due to magnetic field, now energy level. So, energy level will change. Okay. So, how much it will change, that will depend on this term. Basically in this term m l and m s is there. So, value of m l and m s will control the change of energy level due to magnetic field. Okay. So, now for this spectral lines is basically the transition between two energy levels, right. So, energy of the spectral lines will be del E equal to say E n dash minus E n plus mu b b m l dash minus m l plus 2 m s dash minus m s. Okay. So, now if we apply selection rule, so you know this selection rule delta del m s equal to 0 and del m l equal to plus minus 1 and 0. So, del m s, so transition only possible when del m s equal to 0. So, we can now this term will not contribute m s dash minus m s. Okay. So, only transition possible when del m s equal to 0. Okay. So, this term is basically we can put 0. So, ultimately our term will be del E equal to this E n dash minus E n plus mu b b del m l, where del m l equal to 0 plus 1 minus 1. Okay. So, in terms of frequency, Larmor frequency, because when you apply magnetic field, now this your L and S, it basically it will precess around this, it will precess around the magnetic field. Okay. So, this precession frequency of this precession is called Larmor frequency. Okay. If Larmor frequency, if it is nu L, so energy will be h nu L. So, this h nu L equal to E h cross b by 2 m. So, this yes. So, this is coming from as we have seen earlier. So, this is the Larmor frequency and corresponding energy. So, nu L will be equal to E h cross B by 2 m h. Okay. So, this h we have taken down. So, this in terms of frequency of the spectral lines one can tell yes. So, basically as yes. So, that del u equal to h nu. So, in our case del u equal to this. So, this the before applying magnetic field. So, original spectral lines one can see tell. So, that we can write as a original frequency nu 0 plus nu L del m L. So, this mu b is nothing but E h cross by 2 m. Okay. So, this mu v and then b is there. So, this is nothing but nu L. So, h nu L. Okay. So, I think this h nu L. So, that h will go when we will express in terms of energy, and that is why we have written here mu b b. So, this is giving in terms of frequency that nu 0 plus nu L delta m L. Okay. So, this in terms of frequency or in terms of energy one can tell about the spectral lines in presence of magnetic field. So, obviously, you can see that delta m L is 0 plus 1 minus 1. So, when it is 0, so that means this is the original line nu 0 before applying magnetic field whatever the spectral line. So, that will be there. Now, plus minus 1, okay, this one, then nu 0 plus minus nu L. So, that means another 2 lines we will get which will have higher frequency by nu L and lower frequency by nu L. Okay. So, basically we will get 3 lines. Originally it was one line having the frequency nu 0. Now, without applying magnetic field. So, after applying magnetic field we will get basically this one line will be splitted into 3 lines, and out of these 3 lines one is original line and other is 2 more lines. Okay. So, this transition basically for delta m L equal to 0. So, whatever this line will get, so that is called the pi lines, and for delta m L equal to plus minus 1. So, that line is called sigma lines. So, in terms of basically polarization is pi and sigma. So, here we can see this any line basically it will be splitted into 3 lines in strong magnetic field, and that is why these 3 lines basically it is called the Lorentz triplet. Okay. So, this type of splitting is called normal Zeeman effect. Now, question is to see the normal Zeeman effect. So, magnetic field has to be very strong. How strong it is? B has to be greater than Z to the power 4. Now, in case of hydrogen atom, so Z is 1, right. So, in case of hydrogen atom Z is 1. So, that means minimum you need 1 Tesla field, Z to the power 4 means 1. So, you need 1 Tesla field. Okay. So, now in case of helium Z is 2, that means you need J 2 to the power 4 means 16 Tesla. For next one for lithium 9 means 27, not 27, 64 Tesla. So, these are very high magnetic field, and it is impossible to get this very high field in laboratory, because generally from electromagnet we get field around maximum field we get around 2 to 3 Tesla. So, if you want to get more than 3 Tesla in lab, so we use the superconducting magnet, and superconducting magnet also it has generally we get field less than 50 Tesla. Okay, more than 50 Tesla, I think it's I don't know. Generally, it's 30 to 50 Tesla maximum magnetic field we can get from superconducting magnet. So that means that to see the normal Zeeman effect in laboratory, it is practically impossible for atoms of higher atomic number. Even it is very difficult to see for lithium atom Z equal to 3. So, for helium atom also it is also difficult because you need 16 Tesla. So, only for hydrogen atom one can see, still you need more than 1 Tesla magnetic field, 1 Tesla field also quite high. So, but if you see in laboratory, we see we demonstrate the normal Zeeman effect using the normal magnetic field less than 1 Tesla magnetic field, and for that generally we use mercury, neon. Okay. So, Z is very high. So, how we see the normal Zeeman effect. So, in this case normal Zeeman effect we see because here we have to you remember that when we consider this Hamiltonian, then I told this in very high magnetic field, this HB dash term, magnetic interaction term is very high compared to the LS coupling term, HLS dash. So, that means LS HLS, that term is very small. So, it is negligible compared to HB term. So, it is we have not considered the LS coupling. That means, LS coupling, if LS coupling is vanished in a atom. Okay. So, that means, LS coupling, that term is 0 or very small, then only one can see the normal Zeeman effect, and in that case field has to be that HB term has to be higher than the HLS term. Okay. So, now if HLS term is itself is 0, is vanished, means if LS coupling is not there, then that will show the normal Zeeman effect. Okay. So, that is the ultimate consideration for normal Zeeman effect, and if I find some atom where this total L or total S is 0, one of them or both are 0. Okay. So, in that case LS coupling will not be there. So, that atom will show the normal Zeeman effect, and that is why this in case of neon, in case of mercury here I have written in case of neon, in case of mercury, yes, generally we use in lab to demonstrate the normal Zeeman effect. For this neon, mercury, you can check that their L or S or both are 0. Okay. So, that is why this atom shows the normal Zeeman effect. So, basically next I can show you that yes. So, next we can choose the intermediate field, it is not very strong, it is not very weak. So, then what will happen? So, then we see whatever we see this effect of magnetic field, again this is Zeeman effect, it is not called Zeeman effect, it is discovered by Paschen-Back. So, it is called Paschen-Back effect. Okay. So, in this case H is the magnetic field is intermediate field and H LS dash is appreciable, but it is still small compared to this magnetic interaction term. That means, LS coupling term I cannot neglect, but it is small compared to this magnetic interaction term. So, this field is intermediate field, and it is not very strong field, it is not very weak field. So, it is a intermediate field, and for that this interaction term is higher, but it is higher than this Ls coupling term. So, but Ls coupling term that we cannot neglect, because it is close to that this magnetic interaction term. Okay. If it is the condition, then our Hamiltonian will be H equal to H 0 plus H b magnetic interaction for H b dash plus H Ls term. Okay. Now, here 3 terms are there. So, again using perturbation we have to solve it. So, during perturbation you have to choose unperturbed term and then perturbed term. So, this is the unperturbed term, I can take this one. Generally unperturbed term we take if we choose in such a way that the solution of this unperturbed term is known, and that solution, that wave function and its energy will be used for the for calculating the perturbed term. Okay. So, here unperturbed term we have taken H 0 plus H b dash, because already for normal Zeeman effect the solution of this one is known to us and wave function energy is known to us. So, what was the energy for that? So, it was E equal to E n plus m l plus 2 m s then mu v p, and wave function was psi equal to psi n l m l m s. Okay. So, an unperturbed this is perturbed term H L s. So, that from Dirac Hamiltonian or Dirac and that using that Hamiltonian, that from Dirac solution, this we know this term if we calculate this perturbed term. So, this it's we have seen from Dirac solution, that is basically from Dirac equation Hamiltonian, you know, then we found this E n and this other 3 correction energy, and total energy was this. So, other correction energy, this one a del E 1 was for relativistic, del E 2 for the Ls coupling term, and del E 3 it was for the Darwin term. So, what is the del E 2? So, del E 2 is basically minus E n z square alpha square by 2 n l l plus half l plus 1 into plus L for j equal to L plus half, and or multiplied into minus L minus 1 for j equal to L minus half. Okay. So, so basically del 3 term, del 2 term, this is the solution, this is the solution. So, that we can use here. Okay. So, and this is valid for only valid for L equal to L is not equal to 0. Okay. L equal to 0, this vanish. So, this term, so the solution is this type of solution. So, considering this solution, so but this solution was not was for this hydrogen like atom without magnetic field. Okay. So, now this we have included here. So, here this term we have to consider as a unperturbed term, and its wave function we have to consider for to calculate this perturbed term. So, in this case this wave function is psi n l m l m s. Okay. So, considering this one, so this energy for unperturbed term plus from here you can just here this we can take as a lambda n l, because it depends on n and l. So, we have written lambda n l plus into m l m s term. Okay. So, this will term when this is because as I mentioned that this is for this the Hamiltonian, and this is for here we are considering for in presence of magnetic field. Okay, that is applied along the z direction. Okay. So, L is there. Now, if we consider the direction along the z, so basically that quantum number along the Z. So, that in case of L, so that gives ML, in case of S that gives MS. Okay. So, so from here basically directly we are not using. So, this we are here from this Dirac Hamiltonian, there whatever the solution we have got. Now, that solution, that type of considering the similarity, the solution here also solution will be similar, but not exactly same, because here magnetic field and we have to consider since it is along the Z direction, we have to consider the Z component. Okay. So, that Z component quantized along the fixed directions in case of L and S. Okay. So, that is that in terms of ML and MS we have to write. So, that is why this term will be basically some constant term and this ML MS. So, this lambda NL is nothing but this term. Okay. So, except this L minus 1, I think this term we have defined lambda NL, this considering this similarity, it will be this term. Okay. So, from here you can tell lambda NL, it depends on N value and L value. So, it depends, it is independent, it is not independent of L. So, earlier here whatever energy we got, so that there I will discuss. So, that basically gives 3 splitting, 3 lines, one line gives 3 lines. Here due to these terms, so here some what is called symmetry was there. So, that is why we get all the time 3 lines, although 6 transition, 9 transition is possible, 9 lines would be possible, but due to the symmetrical splitting. So, these 6 lines or lines is basically energy of some lines are same. So, that is why these lines are not different lines, same line. So, but when this degeneracy will removed, so then we could get more number of lines, and that is what happening here in this case, that degeneracy will be removed due to this term and we will get more number of splitting. So, I will stop here, I will discuss in next class. Thank you.